Assalamu alaikum. We're doing notes for section 5.2. Make sure that you tape this into your notebook. So we're going to start with a couple of definitions. Since a triangle has three sides, then it naturally will have three perpendicular bisectors. Perpendicular bisectors. Literally one perpendicular bisector for each side. So we pause right here and look at the picture right here. For this side, side AB, the perpendicular bisector would be this little red piece right here because it meets both criteria that number one, it's perpendicular, which means it makes 90 degrees. So there's the 90 degrees. And then bisector means that it cuts AB in half. So where it made that 90 degrees, that point is right smack dab in the middle from A to B, which means that we get this length right here is exactly the same as this length right here. And we repeat that for all three sides. So for this side BC, the same thing happens again. We're going to find the middle from B to C is right here. And then the line that is drawn is right at an angle that makes 90 degrees. And then the last side AC, the same thing happens, that if you look at this red bit right here, it's hitting exactly in the middle of A to C, which means this piece is the same as this piece, and it forms a 90-degree angle at the place where it hits. And so if you extend out all three perpendicular bisectors, if you extend this one out, and you extend this one out, and you extend out the first one that we saw right here, it happens so that they all meet at one point, okay? And so we're going to start right here. When three or more lines intersect at exactly one point, these lines are said to be concurrent. So in this case, this green line, this yellow line, and this pink line are all concurrent because they met up at one place. Just note that this definition can be used for three or more lines. So I could have like one line, two lines, three lines, four lines. As long as they meet up at one place, these lines are said to be concurrent. And the point of concurrency, so the point where they meet, is the point where they touch, where they intersect. Okay, so that would be the point they intersect at. This will be the point to intersect at. Okay, and we're going to do the construction in the class, but you will see that the three perpendicular bisectors of a triangle are going to be concurrent. So when we construct it in class, you will see that it's true that this perpendicular bisector of this segment and this perpendicular bisector of this side of the triangle and this perpendicular bisector of this side of the triangle will end up meeting at one place. So the three perpendicular bisectors are concurrent. And this specific point where they actually meet has a very special name. It's called the circumcenter of the triangle we're looking at. Okay, so that P, if you want to make a little note for yourself, I'll just make a note in the picture. That's called the circumcenter. Okay, this bit that we skipped up here was just giving you a little hint that the perpendicular bisector of the side of each side, we said that it had to cut in the middle, so it was the same length here and here, and it makes 90 degrees. But it just wanted to remind you that if you extend the line out, you don't have to draw this, but if you look at my pen, if I extend it out, it's not necessarily going to cut at the vertex C. So it's not like what you think, that if you extend out this pink line, it'll cut perfectly in B. It won't, because if you continued it, it doesn't cut on the vertex. Okay, so that's just something to keep in mind. The perpendicular bisector of a side of a triangle does not always pass through the opposite vertex. Maybe you weren't thinking that at all, but it's just a little helpful hint, okay? So moving on to the bottom here, we see that we know we have different kinds of triangles. So we have acute triangles, obtuse triangles, and right triangles. And they're just showing you that's what's really cool is like when you're dealing with different triangles, that circumcenter can sometimes show up inside the triangle. So the circumcenter can be inside, like in this case, which means that this red line was the middle of this side and also made 90 degrees. This perpendicular bisector of this side cut it perfectly in half and made 90 degrees. And then this perpendicular bisector of the last side made 90 degrees and also caused this piece to be the same as this piece. And where they are where they intersect is called the circumcenter, and they intersect because the three lines are concurrent, happens to be inside the triangle, okay? If you did the same thing to an obtuse triangle, what we will see is that that point of concurrency, that point where they meet the circumcenter, is outside the triangle when we have obtuse triangles. And then the point, the circumcenter, the point where they intersect in a right triangle is really neat because it happens literally on the triangle. It's right on that hypotenuse in this case, okay? What is neat about the circumcenters for a triangle is if I were to, and you don't have to do this on your note, I'm just doing it to show you. If I were to draw a giant circle around this triangle so that all three vertices of my triangle are on the circle I draw. So literally the circle I draw contains all three vertices. It hits boom, boom, boom. Then what's really cool is the circumcenter actually is smack dab in the middle of this yellow circle that I drew. And if I were to do the same with this obtuse triangle, creating a circle that would end up hitting all three vertices, it doesn't look like it in my picture, but the circumcenter actually is smack dab of that yellow circle. And the same thing happens to an acute triangle, that if I was to circumscribe the triangle in a circle, then the circumcenter is actually smack dab in the middle as well. So we are going to reiterate this on the next page of your notes. So the circumcenter of triangle ABC, so it's showing you an example of the random triangle here, okay, and this is the circumcenter that they already found, meaning that this was the point where the perpendicular bisector of this side, so I find the middle and make sure that it makes 90 degrees of that side, and then I do the same on this side, find the middle, and I would do this with real math instruments in real life, but just showing you that if I found the middle was here and then made sure it made 90 degrees and did it to the last side for side AC, find the middle where it's the same on this side and this side, and make sure I drew a 90-degree line. The point where they meet, okay, the circumcenter of triangle ABC is, in fact, the center, smack dab in the middle of its circumscribed circle. So here is the circumscribed circle because it's a circle that literally contains all the vertices of the polygon. Okay. So a circle that contains all the vertices of a polygon is circumscribed about that polygon. Okay, we'll practice more in class and see how to apply this to problems. Okay, so now that we've gone through all the definitions, I want you to flip back to the first page of notes and let's actually talk about what this theorem is saying. So now that you know what a circumcenter is all about and how we found it, because it was created by this perpendicular bisector of this side and the perpendicular bisector of this side and the perpendicular bisector of this side, this theorem states that if you go from this circumcenter, P, and you walk yourself to one of the vertices, okay, and then you walk yourself from this P to the other vertice, and you walk yourself from P to the last vertice, these three distances are actually all going to magically be the same. Okay, so that is our circumcenter theorem. We will actually practice more in class and how to apply that theorem, but for now we're going to move on to the in-center theorem. So go ahead and draw a squiggly line across your page, okay, and the in-center theorem deals with our angle bisectors, okay? So we'll start right here. A triangle has three angles. We know that. Here's an angle, here's an angle, here's an angle. So naturally, it can have three angle bisectors. Okay, so if I look back down at my picture, for this angle right here, I can have an angle bisector cutting angle A and creating two smaller angles that are congruent. And for my angle B right here, I can have an angle bisector that cuts angle B in half and gives me two congruent angles. And for angle C right here, I can cut it in half and get two congruent angles. And the angle bisectors of a triangle are also concurrent. So think back to the definition of concurrent that we talked about on the first page, and what that means is if I extended this angle bisector out and kept going with this green dot and kept going with the pink line I made and kept going with this yellow angle bisector of angle C, they will eventually all meet up at one point because these angle bisectors are concurrent. So we named this point P. Okay, if P was created by angle bisectors now, not from what we were doing earlier, which was perpendicular, we used perpendicular bisectors earlier, but this is an angle bisector. So if they were made by angle bisectors, then this point of concurrency is called the in-center of the triangle. Triangle. Okay, and so the theorem is really getting at the idea that if you walk yourself from point P to each side of the triangle, those distances will be the same. So if I walk myself from P to side AB, remember that the distance from a point in a line is literally the fastest way there, and the fastest way there literally creates a 90-degree angle. That's what this little blurb down here is reminding you about, that the distance from P to the line segment BC, the shortest way happens to also be the way that makes 90 degrees, and from P to this last side AC, you drop it down straight so it actually does make 90 degrees, and this is actually equal to this is actually equal to this. Okay, that's what the theorem talks about, and we'll deal with examples in class. But they show you here that unlike what we talked about earlier, unlike the circumcenter, where if you recall the circumcenter was created by perpendicular bisectors, where it cut the sides, not the angles, okay, unlike the circumcenter, the incenter is always on the inside of the triangle. So it doesn't matter if it's acute, okay, if I cut this angle in half and kept going, and I cut this angle in half and kept going, and I cut this angle in half and kept going, where they meet up ends up in the middle for an acute triangle, ends up in the middle for an obtuse triangle, I mean not middle, sorry, inside the triangle, ends up inside the triangle for obtuse, for acute, and even for right triangles, the incenter will end up inside the triangle, okay? And what's neat is if I draw a circle, not around the triangle, okay, but if I actually draw a tiny circle inside the triangle, a cool thing happens. So down here, the incenter is the center of the triangle's inscribed circle, okay? So what that means is an inscribed circle is a tiny circle that you get to draw inside the triangle, where literally the edges and sides of the circle touches each side of the triangle. So if I drew an inscribed circle for this triangle, the incenter is actually going to be the center of that little circle, and the incenter here also happens to be the center of an inscribed circle for a right triangle too. Okay, so a circle inscribed in a polygon intersects each line that contains a side of the polygon at exactly one point. So what that means is an inscribed circle is going to hit up each side of that shape it's inside at exactly one place. So it hits up right here, and right here. Okay? All right, we'll practice more in class and go ahead and jot down any questions you have.